Okay, so with this problem, you need to remember that you only have a certain set of skills, right? So you have to look at this problem and you have to think, okay, well, I know I can't plug -1 in, so what's my options? There's no multiplying by the conjugate, there's none of that stuff. But what you can do is factor, right? So factor. Well, then you look at the numerator and you're like, yeah, but I don't know how to factor that. And you're right, you don't. But there are other ways to know if the denominator is a factor of this polynomial, and that's synthetic division. So I can go to the side, and I can do synthetic division. So remember, -1 goes in the box, comes from here, the opposite, it's the 0, right? So then the coefficients go across the top, which are 1, 3, -1, 1, and 4, making sure you don't miss any. So 4, 3, 2, 1, and 0 are my exponents. You drop the first term, 1, and then you multiply. So -1 times 1 is -1. 3 plus a -1 is 2. -1 times 2 is -2. Add -3, multiply 3, add 4, and -4. And that is kind of what we expected because there's really not a whole lot else you can do with this problem. So I have the limit as x approaches -1. So I know x plus 1 is a factor. And then what's left is the rest of my polynomial, and it drops by a degree. So x cubed plus 2x squared minus 3x plus 4 all over x plus 1. Now, of course, at this point, you know that anything over itself is 1, so you can get rid of those. And then you have the limit as x approaches -1, x cubed plus 2x squared minus 3x plus 4. Now, this is just a polynomial, so we know that it's nice and continuous at -1. It's nice and continuous everywhere. That's just a property of polynomial functions. So we add in or sub in our -1, so -1 cubed times 2 times -1 squared minus 3 times -1 plus 4. And we do a little math, and we get 8. And that's our limit. One thing I do want to point out is make sure that you drop the limit here, because when you do the subbing in, that is you evaluating the limit. So there should be no more limit there anymore, okay? So let's look at the next problem. So the limit as x approaches 0 of 5 over x squared plus x minus 5x. So a couple of things kind of spring to mind when I look at this problem. First of all, I know I can't plug in 0. There's not really a lot of factoring that can be done here, except in that first denominator. So basically, you're left with a couple of choices. So algebraic manipulation, whether it's factoring, reducing, putting two things and making them one, taking one thing and making it two. So algebraic manipulation is usually your friend. That's what you go to. So if I see two items, so two terms, I'm going to do my dead level best to make them one term and see what happens. So the first thing I'll do is factor that denominator. So I have x as limit as x approaches 0 of 5 over x times x plus 1. And you do this just to make sure that you're not multiplying by more than what you need. So they both have an x, but this one needs an x plus 1. And what I do to the bottom, I have to do to the top. So I have the limit as x approaches 0 of 5 over x plus 1 minus 5 times x plus 1 over x times x plus 1. So now we have a common denominator, and I can combine like terms. So I have as x approaches 0, I have 5 minus 5x minus 5 all over x, I forgot my x here, x times x plus 1. So I have the limit as x approaches 0. So 5 minus 5 disappears, and I have negative 5x over x times x plus 1. So then, now these x's go away, and I have the limit as x approaches 0, negative 5 over x plus 1. And now, this is not, let's take a second to understand that this is not a continuous graph. It's not continuous everywhere. It's not continuous at x equals -1. But that has no bearing on me finding this limit because I'm not approaching -1. I'm approaching 0. And this function is definitely continuous at 0. 0 is definitely in the domain of this function. That means that I can do straight substitution, right? So I have -5 over 0 plus 1, which means that my limit is -5. Okay. So we have the limit as h approaches 0 of 1 over h. So this is a similar sort of idea that I have these kind of multiple terms and I need to write them as one term. So you have a couple options. You can here combine these first and then distribute. You can distribute and then combine like terms. Totally up to you. We'll go ahead and combine like terms first and then distribute. Okay, so we have the limit as h approaches 0 of 1 over h. So I'm going to make what's inside the parentheses one thing. So that means this one needs a 2 and this one needs a 2 plus h. Right? So we have then 2 over 2 times 2 plus h minus 2 plus h over 2 times 2 plus h. So I have the limit as h approaches 0 of 1 over h, and then combining like terms, 2 minus 2 is 0. Don't forget to minus h, so I have -h over 2 times 2 plus h, and then these h's will disappear. I have the limit as h approaches 0 of -1, so don't forget about your negative, over 2 times 2 plus h. So then the question becomes, well, is that continuous at 0? And it absolutely is. So if it's continuous at 0, then I can plug and chug. So I have -1 over 2 times 2 plus 0, which is -1/4. So again, algebraic manipulation, your absolute best friend. Absolute best friend. Okay? So we have this problem, and I think you all know why I included this problem, because you struggled so much with factoring. This definitely does factor, so we have a difference of cubes, a difference of squares, and then a sum of cubes in the top. So you have to know your factoring rules. So I have the limit as x approaches -2. So you take the cube root first, so x plus 2. So the cube root of x cubed is x, the cube root of a +8 is a +2. And then we SOPs that thing to get our trinomial. So our trinomial is square of the first term, opposite sign, product of those two terms, 2 times x, plus the square of the last term. And then the bottom is the difference of squares. Those are conjugate pairs. Okay. Then at that point, those two go away. And I'm left with the limit as x approaches -2 of x squared minus 2x plus 4 all over x minus 2. Okay, no longer is this discontinuous at -2, so I can plug and chug. And I get -2 squared minus 2 times -2 plus 4 all over -2 minus 2, which gives me 12 over -4, which is -3. Okay, we have the limit as x approaches infinity. So our key here is infinity. So really, there's only a couple things that can happen. When you're talking about infinity, you're talking about the right-hand end of a function. Okay, so as x approaches infinity, that means as I'm tracing my finger to the right for x, what is happening to the function? Is it going up infinitely to infinity? Is it going down infinitely to negative infinity? Or is it approaching some kind of horizontal asymptote? Okay, so those are your three options. Is it getting continuously bigger, continuously smaller, or is it approaching a horizontal asymptote? Now, if you remember your rules for horizontal asymptotes, you know that little over big approaches 0. So we already know that this is going to approach 0. The closer and closer that we get to, or the bigger and bigger that x gets, the smaller and smaller that quantity will be, which means it's approaching 0. Now, we know that mentally, okay, but we have to be able to show that algebraically. And how we do that is we always divide by the highest power in the denominator, which in this case is this x squared. So I have x approaches infinity. 3 over x squared minus x over x squared, all over 4 over x squared plus x over x squared plus x squared over x squared. Okay? So I'm going to simplify. So 3 over x squared minus 1 over x, all over 4 over x squared plus 1 over x squared plus 1. Okay? Now I can evaluate. So I have the limit. Well, I'm going to not do limit. So let's look here. As x approaches infinity, that means that this denominator is getting larger and larger and larger with that bound. So what is that number going to go to? Well, 0. So is the second one, the first one in the denominator, the second one, and of course the limit of a constant is that constant. But 0 divided by anything is 0. Now, again, this is something we already knew, but we had to show it algebraic. So let's look here. Here's that function graphed, okay, and watch what happens as we move to the left. So we've crossed the axis, and then we're coming back up to it closer and closer and closer and closer, and it's never going to touch, but it's going to get infinitely closer, okay? So we have another limit at infinity. So again, if you remember your asymptote, horizontal asymptote rules, you'll know that big over little means this is getting large without bound. So it's not going to have an asymptote. So that means this is either getting infinitely larger or infinitely smaller, okay? It's either going down toward negative infinity or going up toward positive infinity. So we just have to figure out direction. So now there are ways that you can double check this. Just using straight up algebra. But remember, we're going to divide by the highest power in the denominator, which in this case is x cubed. So we have 4x to the 4th over x cubed plus 5x over x cubed plus 1 over x cubed all over 37x cubed over x cubed minus 9 over x cubed. And then we'll simplify the limit as x approaches infinity of 4x plus 5 over x squared plus 1 over x cubed over 37 minus 9 over x cubed. So then we can evaluate this limit. Now here is the thing. This term right here, as x gets infinitely larger, this term is getting infinitely larger. Okay, it's not going down, it's definitely going up. As x gets bigger and bigger and bigger, 4x is going to get bigger and bigger and bigger. So technically we get this infinity plus 0 over 37 minus 0. Now that divided by 37 is negligible when you start talking about the very ends of function. Now we know that there is no necessarily an end to a function, a definitive end. But when we start talking about, 1,000, 10,000, 100,000, a million out there to the right, that 37 is absolutely negligible, and we get that the limit is going to positive infinity. Now, if you get into a situation like this where it's either approaching a positive infinity or negative infinity, and you're not sure whether the function is getting infinitely larger or infinitely smaller, you can just plug in some values. Plug in like 10, then plug in 100. And then if you're still not sure, plug in 200 or 1,000 and see what is happening to those numbers. Are they getting bigger? Are they approaching larger numbers? Or are they going infinitely negative? So larger negative numbers, okay? It's a very simple, quick test that you can do if you're unsure of your math logic, let's say. You can check it algebraically just by plug and chug some numbers. Be like, oh yeah, that obviously goes to infinity, okay, or negative infinity. So I did the same thing. So there's the function. Here's the weird graph. It has a slant asymptote or an oblique asymptote. And watch what happens as we scroll to the right, which is x approaches positive infinity. So it gets infinitely larger. There I am around 700. It's infinitely larger as x gets infinitely larger. So it's definitely approaching positive infinity. Okay, so last one. There we go. Wouldn't let me move. So we have the limit as x approaches negative infinity of this root. Okay, so it's a cube root. So a couple things that you need to remember is that we can move a constant in and out of a limit. That's one thing that we can absolutely do. The limit of a root is the root of the limit. So if you have just a part of a root in your limit, then that's probably going to be one of those multiply by the conjugate things. But this is definitely not that case. The whole root is the limit problem. Therefore, the root of the limit is the limit of the root. So be very cautious with this because it needs to be, the whole problem has to be the root for this to be a true statement. So I can say then that the cube root of the limit as x approaches negative infinity of x minus 3 over 5 minus x. Now we know algebraically that there is a horizontal asymptote here because this is same over same, and it is the coefficients of the highest power, so 1 and 1. So 1 over negative 1 is negative 1. So I already know my answer is going to be negative 1, but I need to figure out algebraically how to get there. Okay, so again, you always divide by the highest power of the numerator. So I have the limit as x approaches negative infinity, cube root. So x over x minus 3 over x over 5 over x minus x over x. So I have the cube root, the limit as x approaches negative infinity of 1 minus 3 over x over 5 over x minus 1. So I have the cube root. So we're ready to evaluate. So the limit of a constant is 1. The limit of 3 over x as x gets infinitely large is going to approach 0 because the 3 over the x, so you're talking about 3 over 1 versus 3 over 10, 3 over 1,000, 3 over 1,000,000. Super, super small, right? So 0. 5 over x, the same thing, 0. And then the limit of a constant is 1. So we have the cube root of 1 over negative 1, which is negative 1. And the cube root of negative 1 is 1, or negative 1. Okay, there's one more I just need to add very quickly. We have the limit as x approaches 0 of 2 to the x times sine x all over x to the 4th. So there's no way that I can factor this. There's really not a whole lot I can do other than, again, algebraic manipulation. So I can write this as a product. So the division, the quotient rule, the limit of the numerator, or the limit of the quotient is the quotient of the limits, only works if the limit in the bottom doesn't approach 0, and this one does. So I can then turn around and use the product rule if I write this as a product. So I have the limit as x approaches 0 of 2x plus sine x times 1 over x to the 4th. Now I have a product, and I can use product rule because there's no restriction on product rule. So that means that the limit of the product is the product of the limit. So I have as the limit as x approaches 0 of 2 to the x plus sine x times the limit as x approaches 0, 1 over x to the 4th. So this first one is super easy. Both of those functions are continuous at 0. Nice, beautiful little functions. So we have that the limit as x approaches 0 of 2 to the x. So that means 2 to the 0, which is 1, plus sine of 0 is 0 times, now we have the limit as x approaches 0 of 1 over x to the fourth. Now we've done this in a bunch of different ways, but remember, as we get closer and closer to 0, okay, this is not infinity, this is 0. I'm getting super small numbers. And when we divide by a fraction, so just as a note here, we're going to make a note that when you divide by a fraction, so that's 1 over 1/2, which is 1 times 2 over 1, which is 2. So then you get 1 over, let's say, 1/20. It's going to be 20, 1 over 200. So I'm getting infinitely closer to 0, and my output is going up because I'm multiplying by the reciprocal of that fraction. So that means that that is approaching infinity. Now, we can't really do math with infinity, but understanding the concept that 1 times anything is itself, but even if this had been, let's say, 7 is negligible, or even 1/7. 1/7 is negligible when you're talking about the concept of infinity. You know, again, 1,000, 1,000,000, 100,000,000, 1,000,000,000, 1,000,000,000,000. We're talking about extremely large numbers at the very ends of this function. So my answer would be infinity. Okay?